Okay, so Margret Heinze will talk from TU Munich. We'll talk about enhanced noise resilience of the surface-GKP code via designed bias. Yep, there it comes.
Yeah. So,
okay, take it away.
Thanks a lot first to the organizers for having this conference, or making this conference possible, this workshop, having the possibility to listen to interesting talks. And thanks also for giving me the opportunity to talk here about recent research together with Lisa Hengli and Robert König on the surface-GKP code and how we can enhance noise resilience of this code via designed bias. So our general question was, one has to be careful with Gaussian quantum error correction because there exists many no-go results on how well Gaussian encodings or Gaussian error correction can correct even for Gaussian errors. And in the special case of the GKP code, this takes the form that Gaussian encoding of the GKP code cannot improve noise tolerance of this code. And we asked the question whether this still holds when we concatenate the GKP code with another code, or more specifically, can we use a Gaussian encoding of the GKP code to enhance noise resilience of the surface GKP code. So let me first tell you what I mean by a concatenated code. So we are given an inner quantum error correcting code B, where I write this here for the quantum error correcting code. So as usual, we're given an encoding map, a noise channel, and also a recovery channel, which in our case, as we deal with stabilizer codes consist of syndrome measurements, followed by correction operations and an inverse encoding. And as I mentioned before, we also want to concatenate this code with an outer code so that we are also given an outer code A, such that every of these inner code channels now gives us a noise channel of this outer code. And in our case, we consider as the inner code the GKP code and the outer code the surface code. So the surface code encodes one qubit into many qubits, where each of these qubits is now not a physical qubit, but again an encoded GKP qubit. So in this context, this question is, can we use a Gaussian encoding of the GKP code such that this effective noise on the level of the surface code is now one that the surface code is especially tolerable towards? And would this then in the end improve the error resilience of the surface GKP code? So in the first talk today, we already heard that there are noise models where the surface code is especially tolerable towards, namely these biased codes. So for the next, I try to hurry up a bit because we're a bit late, 20 to 30 minutes. I will first present you these biased noise surface codes, then the GKP code, the other ingredient, and tell you how we design bias of the resulting error model by introducing something we call asymmetry or asymmtric lattices. And then we look at our numerical results of simulations of the asymmtric surface GKP codes at the end. So you already saw this today. This is the advantage of the last speaker. Maybe we can gain a bit time again. We're considering the square lattice surface code. So we're considering a D times D surface code with what we call smooth top bottom and rough left-right boundary conditions, which is as usually placed on a two-dimensional surface on a lattice of D square horizontal and D-1 square vertical edges, where we place the physical qubits on the edges of this lattice. And as usually, the stabilizers are these star and plaquette operators, and the logical operators are these strings of physical X and Z operators. So here we again look at the X and Z stabilizers, but in the end, actually, we'll deal with the same issue as in the first talk. So we rotate our blocks wheel later, so you already know what will happen. And this code encodes one logical qubit into these n physical qubits and gives us a distance d code. And we can now look at noise models where this surface code is very tolerable towards. And to analyze the performance of these codes, we always have to look at a decoder. And the decoder that we look at is the maximum likelihood decoder. So we're given a Pauli noise distributed according to a probability distribution P. And for every syndrome, we pick a representative error. And as always, the maximum likelihood decoder is the decoder where we pick as a correction operation the error which has happened with the highest probability, or one of the errors which has happened with the highest probability, so that the resulting logical error rate, which I now call PR here, is given by this form. And when we later go to the numerics, we have to compute these coset probabilities of this form, which is generally very inefficient and complicated. So we use the so-called BSV decoder to approximate the maximum likelihood decoder. I will not go into detail, but it is it depends on the parameter chi, or the bond dimension. And for chi to infinity, it approximates the maximum likelihood encoder. And the basic idea or insight is that this quantity here can be represented as a contraction of a tensor network on this surface code, which can be efficiently computed. So now we look at biased noise models. So generally we consider IID noise, so noise on which is equal on all or equally likely on all qubits. And as before, the bias is defined as the fraction between the more likely noise and the less likely noises. Now here the Y noise is more likely than X and Z noise. And these authors here showed that the surface code can tolerate more noise if the Y noise is more likely than the X and the Z noise. So the unbiased case corresponding to eta equals 1/2. They found the usual error threshold of around 19%. And in the infinite bias case, this error threshold of 50% can be obtained, interpolating in between, if you maybe remember the results or the plots from the first talk today. So we have found the noise model that we want to design our GKP code now towards. So we want this GKP qubits in the end to give us noise models with one error probability higher than the others. So we want to, and not anyone, we want to have the Y noise bias towards the other two noises. So the next question would be, can we design this, and if whether this improves the error resilience. So now we come to the GKP code. I can maybe be a bit quicker now. Encodes one or several qubits into harmonic oscillator modes or bosonic modes. or these continuous variable systems that we consider only one mode with this Hilbert space of square integrable functions. Operations can be described by these quadrature operators Q and P, which satisfy as usual the commutation relations. And the nice thing that we will use is that we can use this phase space representation for many purposes, where we consider the two-dimensional phase space between these momentum and position operators. And Gaussian unitaries, which we use for our Gaussian encoding of the GKP code, act on these quadrature operators as would symplectic affine transformation act on phase space vectors. One example that we will use later is a squeezing operation, which would deform a quasi-probability distribution looking like this into a squeezed version, squeezing along one axis and in the other direction along the vertical axis. And the other interesting or useful transformation that we use is displacement operations, which just correspond to phase space displacements, therefore also the name. They displace phase space vector by an amount of this vector psi. And the GKP code is designed towards this displacement noise. So noise is now that every error is a displacement, which now can be picked according to some probability density function f. For our purposes, it is useful to define the GKP code using the so-called symplectically integral lattice. So on phase space, we define a symplectically integral lattice by being spanned by two vectors L1 and L2. So we are in two-dimensional phase space. If these two vectors satisfy this relation, where this here is the symplectic inner product. And we can similarly define a corresponding dual, symplectically dual lattice, which we call L_perp, which is spanned now by two vectors, which are in relation to the spanning vectors of the original lattice via this relation. And we can use this to define GKP codes. So the simplest example that we think of, and actually that we consider a lot, is the square lattice GKP code. So we're considering the square lattice here, which is spanned by these two vectors L1 and L2. That has this form, and the dual lattice is just with half the spacing, gives us these dual vectors. And then the GKP code is simply the stabilizer code generated by the stabilizer generators, which are just displacements along the lattice vectors. This gives us a code space with this adjoint +1 eigenspace of these stabilizer generators, and the logical operators are elements of the centralizer of the stabilizer group, which turn out to be displacements along the dual lattice. And we usually consider this code under displacement errors. So we displace by a vector mu in R2, and the syndrome measurement corresponding to the measurement of the stabilizer generators just gives us mu modulo the dual lattice. And usually we consider as correction to the nearest lattice point in the dual lattice. To make this more specific, I will just present to you this well-known example of the square lattice GKP code. So we recall the stabilizer generators are displacements along this lattice L, this dark lattice, and the logical operators correspond to displacements along half the spacing of the original lattice. And the code words 0 and 1 are simply these infinite sums of spikes at either 2 times multiples of square root of pi with spacing of the original lattice, or for the logical one at odd multiples of square root of pi. Where we can already see here now in the Q eigenspace, we see that the logical x transforms the 0 into the 1 and vice versa. How does error correction work here? Okay, we can also graphically easily see this in this lattice picture. We're given an error which is in phase space being given by a phase space vector. The syndrome corresponding to measuring q modulo square root of pi and p modulo square root of pi just corresponds to this error lattice vector or error phase space vector modulo the dual lattice, and will be an element of this here, this call it Voronoi cell of this dual lattice. And correction to the nearest lattice point would just be correction by an amount of minus the syndrome that we measured. So for example, if the error is given by some vector here, in this case, the syndrome would be this vector, and correction would be minus this vector. So this original point would be corrected to this lattice point, and okay, this actually gives us an error. More precisely, we can shade our phase space in different colors, where if the error nu is in these blue edge regions, the GKP code can successfully correct for this error. And if it's in the other regions, these gray shaded regions, a respective error will happen in X, Y, or Z error. And now we can see what happens under Gaussian noise. So not only one simple error, but some distribution of displacement noise, where now we assume that this F is Gaussian. So it's actually characterized by this 2 by 2 matrix sigma. What we essentially do to compute the resulting error model of under this noise is we decompose this error distribution F into distribution along the Q axis and the P axis, and we just integrate over these regions which cause no error, and respectively integrating over the regions which cause an error. And this will give us the probabilities, I call it QX and QY, and the resulting error model, which gives us independent X and Y noise, where this QX and QY are these sums of these integrals over these respective parts. And as we can see here, if we take the isotropic case, where errors along the Q and the P axis appear, or displacements along the Q and the P axis are equally likely, then this QX and QZ will be equally large. And we are not in the case of this asymmetric noise that we want to have, where this, because usually if the error is small enough, this Y probability will be smaller than the X and Z probability. So we want to design this bias into this code. And to do this, what will help us is a nice observation when we consider these GKP codes, because every symplectically integral lattice can be written as a symplectically transformed square lattice. So for every symplectical lattice, there exists a symplectic matrix S, so that it can be written like this, and respectively, the GKP code space of this code can be written as a Gaussian unitary times the code space of this square code. So we can now do a bit of computation, which just how these displacements perform or under this, or transform under such Gaussian encodings, to obtain that having asymmetric GKP code, which is given just by a symplectic matrix times the square lattice under symmetric or isotropic noise gives us the same resulting noise channel as if we would have the symmetric GKP code under asymmtric noise. So even if the physical noise at the GKP, the displacements or bosonic level is symmetric, we can make it asymmetric by using this encoding with the symplectic matrix. And the one we choose here is this squeezing matrix. We introduce some squeezing parameter R. We choose it like this because this has a very nice graphical interpretation here. The lattice of this squeezed GKP code or this transformed GKP code, we just squeeze along the Q axis by an amount of, we decrease length and we increase by the same amount square root of R in the other direction. Yeah, and this code gives us now biased noise. Okay, I skipped all the formulas right down, but the main thing is we reach that the rectangular GKP code or the asymmetric GKP code with the squeezing parameter R under isotropic displacement noise now gives us an effective error channel on the GKP qubit, which is now biased towards this Z noise. And with this, we have our ingredients to define our code that we are analyzing. So we consider the concatenated surface GKP code, but we do not just use any GKP code, but we use a square lattice GKP code plus an additional Gaussian unitary encoding. And what do we use? Okay, what I've just presented to you, the Gaussian unitary encoding with this squeezing matrix SR or the squeezing parameter R, which now turns our isotropic Gaussian noise into a biased noise of independent X and Z noise, where it's biased towards that. And okay, then we just rotate our Bloch sphere to make the Y noise more likely than the other noises, to make it compatible with the surface code that we consider. So we just map the Y eigenstates to the Z eigenstates. And this is the code that we analyzed now. So we ran Monte Carlo simulations of this surface GKP codes, where for every GKP qubit, we've independently picked a displacement error according to this Gaussian isotropic distribution F sigma squared. So our noise depends on this parameter sigma, which is just the variance of this error distribution in both directions, Q and P. This we pick as our only noise, so we do not consider measurement errors or other errors. Then we run our GKP symptom extraction and the GKP error correction of this now rectangular or asymmetric GKP code. And okay, then we give this to the BSV decoder for the surface distance D surface code for error correction. So what we have in the end are the error probabilities, logical error probabilities, depending on the parameter sigma, D, and R. So this is our physical error parameter sigma, D the distance of the surface code, and R our asymmetry ratio, which is kind of a measure of the bias. Okay, I've listed the parameters for our simulations. So, but I think I would prefer to the paper if you want to go into details and present you the results now. So here we have this plot of this error parameter for the asymmetry ratio R equals 1, which means just the square lattice GKP code. We have here this blue line, which is just a bare GKP code. So if we would not use any concatenation with a surface code, just a bare GKP code, this would be the resulting error probability. And these lines correspond to different distances of our surface code. And we observe that we obtain a threshold behavior. Okay, this is just an inset with which we computed the threshold value. And then we ran the same simulation for r equals 2. So our asymmetry ratio 2. Here we have two bare GKP lines. One is the bare GKP line for asymmetry ratio r equals 1. So no asymmetry. And then for the r equals 2 asymmetry ratio, for which the rest of the plot also applies. And the two thresholds we obtain are around, for sigma, around 0.54 for r equals 1, which is comparable to similar results. So they're not exactly 100% comparable because they have slightly different error models, or the topological code instead of the surface code. But they are comparable. And we could increase this threshold now to 0.56. And if we go to higher r equals 3, again increases this error threshold slightly. And if we now plot the error thresholds independence of the asymmetry ratio r, we obtain that we plot them as in increments of 1/2 between 1 and 4. And we observe that from r equals 1 to r equals 3, we could increase this error threshold. Which says that both the questions that we had in the beginning are answered by yes. So we can design the surface code such that it gives us a biased GKP qubit noise. And this actually improves the error threshold. But probably the next interesting thing is that the error threshold decreases again. Why is it not monotone with r? And okay, since we ran simulations, we do not have a kind of 100% sure explanation, but the one reason might be that here are two effects which are struggling with each other. First, we increase the bias, which is good and should increase the error threshold. But on the other hand, if we just looked at the bare GKP code with no concatenation, just the bare GKP code, okay, this gets worse as we increase the asymmetry ratio. So this might be an effect of these two effects competing, but it might also be some finite size effects. So we want to analyze this a bit more. Yeah. So okay, the time is nearly up. Okay, maybe a little remark that I want to make. If we compare our results, we in the end just by this asymmetry ratio engineer a certain Pauli noise on the qubit level, which we hand now then to the surface code. And I just want to point out that this is actually a little bit a different noise model than the one considered in these biased surface code noise papers, where these authors considered equal X and Z noise and a bias towards the Y noise. And here we are given independent Y and Z errors, where also these depend on this parameter R in a more difficult way. So both these eta in these papers as well as our R are measures of the asymmetry, but they are not directly comparable. So the limiting case R equals to infinity is comparable, but the way this limit is reached by either eta goes to infinity or R to infinity is a bit different. With this, I would like to summarize. So we, as a first result, we could use a Gaussian encoding to find that the asymmetric surface-GKP code improves the error threshold from around 0.54 to 0.58, where we use squeezing, which depends on this parameter R as follows. So I think around 3 decibel for R equals 3. So these no-go theorems for this Gaussian CV into CV encoding for the GKP code do not longer apply in this concatenated setting, and we can improve these error thresholds. We also looked at the case where we use the GKP syndrome information. So before the simulations, we have not used the GKP syndrome information in the BSV decoder, but we can also compute a probability distribution depending on the syndrome which we hand to the GKP to the surface BSV decoder. And okay, our symmetry results are compatible with these other improvements, other results, where I would refer to the paper. But there are still some questions open. For example, to introduce noise in other parts of our protocol, so to look noise in, for example, the syndrome measurements, other parts, to really understand the monotonicity of these error thresholds with R, which would also mean understand this monotonicity, and also to look at non-ideal GKP states, so these realistic and physical finitely squeezed GKP states. With this, I want to thank you for your attention, and I'm happy to answer questions now.
Okay, thank you, Margaret, for a nice talk. Thanks for also keeping in time a little bit. Okay, Srutu, did you want to ask a question? I don't hear you. You have to unmute yourself, probably. Yeah.
Sorry, sorry. I missed your definition about P error. So when you define P error, is it the failure of the logical lattice, or it's the failure of your GKP state? What is it?
The failure of the concatenated, so surface GKP code.
Okay. So the actual
concatenated. Yeah.
Okay. Okay.
Can I ask a question, Barbara?
Sorry, yes, go ahead.
Hi, Margaret. So the non-monotonicity with respect to R, do you think that this might be due to lack of convergence of the decoder, like maybe not a large enough bond dimension?
Actually, I think not, because we considered a lot of different bond dimensions to be quite sure that it is convergence. Yeah, so we did convergence tests.
You did a convergence analysis and it
Yeah,
seems converged. Okay.
Yeah.
There's a question in the Q&A.
Yeah, I'm just looking at it. Okay, here. Okay, question by Daniel Miller. Do you know if the thresholds would increase/drop if GKP qdits would be used instead of GKP qbits?
Okay, so there's actually a lot of things to analyze there. So we didn't look at these cases, so neither at the at encoding GKP qubits into more than one bosonic mode. So we only looked at this one bosonic mode, one qubit case. And okay, we can go both directions, more qubits into more modes, or qdits into one mode or more modes. We didn't look specifically at these cases. So I would say this is more a first analysis and proof of principle, and maybe now one can look at specific cases that one is interested in.
Okay, thanks. Are there more questions? Maybe some of the panelists or?
There's a question on Slack.
Okay. Maybe I should stop sharing if I want to go to the Slack.
I mean, if Hayata wants to ask a question directly, I can also unmute you.
Did you unmute the question asker?
I can do that right now. I haven't heard back.
The question is about whether or not it's possible to preserve the bias when you have a Hadamard gate. I can read the question out, but maybe that summary, maybe you can say something already.
I don't know, can you maybe read the question out? I'm not sure.
Sure, I'll just read the question.
Mhm.
This is from Hayata Yamasaki. When we perform a logical Hadamard gate on the surface-GKP code by a Fourier gate at the physical level, the bias towards the Q direction in the phase space becomes the bias towards the P direction. A squeezing operation may be used to enlarge the lattice space between Gaussian peaks of the GKP code, but such squeezing also increases the variance of each Gaussian peak. That is, squeezing does not bias X and Z errors of the GKP state. So it seems we cannot keep the initial bias when we perform quantum computation that includes the Hadamard gate. Am I missing something?
This actually might be true, but maybe one thing, the squeezing that we look at is, okay, maybe I should have made this a bit more clear. It's not the squeezing of the ideal versus non-ideal GKP states. It's a Gaussian encoding with a squeezing unitary on the GKP code space. So it is squeezing, but it's something different. But generally, we did not look at computation. So
maybe I can actually add to that answer is that you can actually do computations, you can do universal computations at the logical level without ever actually using a physical Hadamard. So at the physical level, you cannot do a bias preserving Hadamard, and you can prove that. But you actually don't need a physical Hadamard to do universal computation. You can do lattice surgery, which does not require you to do physical Hadamards.
Right, yeah, so you can keep the bias at that logical level by avoiding that. Yes, I agree. Okay, I hope this answered the question. Okay, I think we should stop the session and thank Margaret again for a nice talk. And if people want to chat more, they go to the Slack channel and I'm going to have some dinner. Okay, see you all tomorrow morning, at least for me tomorrow morning.
See you then, bye.
Bye-bye.
Bye. Bye.